Welcome, my dear students. In this video, we are discussing CRC coding. CRC stands for Cyclic Redundancy Code. I am Sandeep Kumar Acharya, and I am teaching computer science and application. So you are watching a video on CRC. I am discussing CRC generator as well as CRC checker. Okay, so let's quickly start it. Here we have a problem. A bit stream 110.1011011 is transmitted using the standard CRC method. The generator polynomial is given as x to the power 4 plus x plus 1. What is the actual bit stream transmitted? So this is the question. So here uh, CRC is a error detection methodology which is done in the data link layer of OSI model. Okay, in this method we are sending a data and appending a CRC code with the data. So sender, before sending the data, it adds a CRC code with the data, then it sends to the receiver receives the data along with the CRC code. Now what is the CRC code? That must be defined by a generator function or CRC generator function at the sender's end. CRC generator function at the sender's end. This computer is sending the data. Which data? This is our data. It is given that this is the data we are sending. And the question is asking what is the actual bit stream transmitted. That means this is the data. So this is the data and we are appending some bits more with the actual data, which is CRC. So what is the actual bit stream transmitted is the combination of these both data and CRC, right? CRC code. So CRC generator function is a process. When we are sending the data, we are generating the CRC with the use of generator function. And at the receiving end, we are receiving the data and the CRC checker function is there. CRC checker function is there, which is checking the data whether an error is there or not. So one more thing is given here, that is a generator polynomial. Okay, which one is x to the power 4 plus x plus 1. Here we have polynomial provided, this one. Here we will further do some operation on it. We will fill the skip part of polynomial, that we know we have a gradual parts of powers. That means x to the power 4, x to the power 3, x to the power square, ax and all. We have all the power. We are representing this polynomial in that form of power division. So x to the power 4 means we can say 1 into x to the power 4. Then we don't have x to x cube, so we must write it like 0 into x cube. Then we don't have x square, so it is 0 into x square, plus we have x, so 1 into x is there, and the next one is 1. We know you can think it like x to the power 0, so here is 1 into x to the power 1. Similarly, something to the power 0 is 1, so we can also represent this one like this. But here is 1, so 1 into x to the power 0 is the same as 1. Okay, you can think about it. So you can see the power is distributed gradually from the high to low. Here from 4 to 0, right? So now we are taking the coefficient only. For x to the power 4 we have coefficient 1. For x to the power 3 we have coefficient 0, like that, 0, 1 and 1. So this is a key. Okay, this is our key. We have got it from the polynomial provided. With this key, we will generate the CRC code. Now, what we will do next? So the key is, I'm writing it again. So the key became 1 0 0 1 for x to the 4, 0 for x cube, 0 for x square, then 1 for x, and 1 for that one. Okay, so this is our key. So we have how many bits in this key? 1 2 3 4 and 5. So 5 bits are there. 5 bits are there in the key. Okay, now we will take one less. That means 5 minus 1, that is equals to 4. One less number, whatever we have in our key, and we will add that much of zeros with this data at the generation of the, for the generation of the CRC. Okay, so we have 1 1 0 1 0 1 1 0 1 1. This is our data part. We will append 4 bits or 4 zeros with it. 1 2 3 and 4, right? Then we divide it with the key. That means 1 0 0 1 1, right? So this is the generator process we are discussing right now. By this we are generating the CRC code. Okay, now what will happen? Okay, we will divide this whole stream of bit by this key. Okay, but here the division method is not a binary division process, but also we are applying here modulo 2 division modulo 2 division method. Okay, in this method we are using XOR gates. Okay, in this method we are using XOR gate. So in XOR gate we all know, okay, uh, 0 0 0 1 1 0 1 1. When it is 0 0, it gives you 0, and when it is 1 1, it gives you 1. That means we know the truth table. Okay, for same bits we are getting 0, for different bits 1 0 or 0 1 we are getting 1. So we must remember this portion before we are applying modulo 2 division. Okay, now this goes for once, so it will be 1 0 0 1 1, right? We are doing the division. Fine. Now we are applying the XOR gating. 0 and 1. 0 and 1 gives you 1. So it is 1. 1 1 gives you 0. 0 0 gives you 0. 0 and 1 gives you 1. This one is 0. Okay. We are not writing the extreme left 0 here for our benefit, for proceeding the next step, or taking the next step. So 1 0 0 1. There are 4 bits. 1 2 3 4 5 bits, 4 bits. So 1 bit is required. So we are taking this one down. Now it is 5 bits. It will go for 1. Okay, 1 0 0 1 1. Okay, so here one point you must notice: it will go for 1 or it will not go. There is nothing to worry about whether this number is bigger, whether this number is smaller than the divisor. Okay, you just look at the matter whether 5 bits are there in this division. That means you are dividing it with 5 bits. So for the divisor you should have 5 bits. So this is the main thing you should keep in mind. Okay, for normal division, there is a different scenario, but for this process, we are focusing on only these things, that the number of bits must be the same. Okay, so here we can see that it is all 0, 1, 1, 0, 0, 0, 0, 0. Fine. So we have left this part. Now we will take normally what, this one down. So it is not going anything, it's not going once. So we are taking this 0, but we have to put a 0 for a division, normal division methodology, to take this 0. So we are putting a 0 before we take this 0. Now we are taking down this 0. Now we have 2 bits, but we have 5 bits to divide it. So we need more bits. So we will take it. We'll take the next one, but before we should put a 0. So next one is available now. Then again, it is 3 bit. We are putting one more 0 and taking this one. Now 1, 2, 3, 4 bits. We need 5 bits. So we need this 0. For that, we are putting one more 0 and taking this 0. Okay. So this is the process. Now it will go once. Now it is 1, 0, 0, 1, and 1. So 1, 0, 0, 1 is 1. This is 0. This is 1. This is 0, 0. So this is 3 bit. We are taking this 0 down automatically or normally, but it is 4 bit now. We need one more bit. We will take this 0, but we have to put 1, 0 for taking this 0. Now we are taking this 0. Okay. So 1, 2, 3, 4, 5 bits is there. So now it goes once. So 1, 0, 0, 1, 1 is the 0, 1 is 1, 0, 1 is 1, 1, 0 is 1. These are zeros. So now we have 3 bits. You can put this 0 down. You can take this 0 down. So we have 1, 2, 3, and 4 bits now, right? There is 5 bits. So it is not divisible anymore. So this is the reminder. Okay, we'll do not take any point and take 0 and all. We'll stop here. Okay, we'll stop here because the digits we here for the divisor is finished. Okay, we'll stop here. So this is the reminder. Okay, sorry, this is the reminder, and this is our CRC code. This is our CRC code. Okay, cyclic redundancy code. So now the generator function is successfully generated this CRC code. So we will replace this 1110 with this CRC code. Like now, what is the actual bit stream transmitted is, okay, what it is, like 11010, 11010, 11011, 11011. This was the data, and along with we were appending this 1110. This is the CRC. So data and CRC together is the actual bit which will be transmitted. Fine. So this is how the generator function is acting. Now at the end, we will check this data by the checker function whether an error is there or not. Okay, we'll do it quickly. We'll do it very quickly. Fine. So at the receiving end, this data is being received. Okay. At the receiving end, we have received this data like 11011011111 and 0. Okay, we will divide it again by this key 10011 at the receiver's end. This is the function of checker. Now we are discussing the checker function. CRC checker function. So 1, 2, 3, 4, 5 bits we are considering. 1 0 0 1 1. Fine. So XOR is what? 1 0 0 1. This one is 0. Simply we're putting it down. 1. Again it is 1 1 0 0 1 1. So it is all 0. We need to, the 1 will be there automatically. Okay, but we need 5 more bits or 4 more bits to make it a 5. So we need this 0. We'll put a 0 here. We'll take this 0. Then we'll put one more 0. And taking this one more 0. Taking this one, 1 2 3 4. We're putting one more 0 and taking this one. Okay. Now 1. So 1 0 0 1 1. Okay. So 1 1 0 1 1 0. This is 1 0 0. We need, it will become down automatically. Then it is a 4 bit, so we need this one. So we are putting a 0 and taking this one. Then it is 1 and we are having 1 0 0 1 1. It is giving you all 0, right? And this will come down automatically as 0, right? But after putting this 0 down, we are not able to go for once again. So we have to put a 0 here because it is not divisible by this anymore, even if we are taking this 0 down. Okay, this is a very important point. You should remember it. If there was no such 0 here, okay, and it is ending like here, so there was no necessity for putting this extra 0. But whenever you are putting this 0 down, and even after that you are not, this bit is not divisible by this divisor, then you have to put a 0 according to the division rule. So this is a very important point, you must remember it. Okay, so now in the remainder section we have got all zeros. Okay, if we get this all zeros at the receiver's end by the checker methodology, then we must say there is no error in the receiving data or received data. The received data is very much in its all forms or correct form. So there is no error. But here we must change the data a little bit as if some error is there. Then what happens? We will check. Okay. Then what happens? We will check. Suppose for this bit stream, okay, we are changing 2 or 3 bits, like uh, we are changing this 2 bit as 0 0. Then that is 0. That is changing this bit to 0. No, we're not changing this bit to 0. We are changing this 0 to 1. Okay. So 0 0 0 is there, 1 is there, and this 0 is replaced by 1. Then 1 1 0. We are changing this to 0, then it is 1. Okay. Then what happens? You check it. It is 0 0 0 1 1 1 1 0 0 1, then 1 1 1 0. So we will divide it by 1 0 0 1 1. Okay, once 1 0 0 1 1. So it is 0 0 0 0 1. It will go once again. So 1 0 0 1 1. It is 1 1 0 0 0. You are putting it down. This one, it is not going because 3 bits is there. We'll make it 5. So putting a 0, taking this one down. 4 bits, putting one more 0, taking this 0 down, right? Now 1 1 0 0 1 1. Okay, so it is 1 0 1 1, right? Taking this 0 automatically down. 1 1 0 0 1 1 1 0 0 1. Putting this down 1 ones, 1 0 0 1 1. Okay, so it is all 0. Okay, then you are, this one will be there automatically. Then we are putting one more 0, taking this one. We are putting one more 0, taking this one. We are putting one more 0, taking this 0. So we have 4 bits. Okay, here is 5 bits. So this stream is now the reminder. This is not divisible by this key anymore. Okay, because it is 5 bit, it is 4 bit. So this is our remainder. Okay, the remainder is not non-zero. The remainder is non-zero. This is telling us, the checker methodology, it's telling us that there are some error in this bit stream received. There are some errors this bit stream received. Okay, so we have watched, or we are now know both the way. If some error is there, what will be the case? The remainder will be non-zero. If no error is there, the remainder will be all zeros. Okay, so this is how the CRC code is working. Okay, thank you for watching. Maybe there will be another video shortly on this same topic of CRC methodology. Okay, so be careful and be focusing on my channel and watch all those videos related with this topic. Keep watching, keep focusing.